This is the second lecture from Chapter 11, and this lecture focuses on the energetics involved in phase changes. In order for a substance to change phases, there has to be a change in the amount of energy present, typically in the form of heat, or in the case when a gas is involved, a change in the pressure. So if we're going from a gas to a liquid or a liquid to the gas, that change is quite sensitive to changes in pressure. But again, most of the time it's a change in the thermal energy. I want to emphasize the importance of understanding what actually occurs on a molecular level when you change phases. First of all, the most important thing is no internal bonds are broken when you change phase. So if you have water as ice, let's say in the solid phase, and you're melting it, you're adding thermal energy, and you're converting it to water in the liquid phase, you have not broken any of these chemical bonds, okay? You started with H2O, you ended with H2O. So it is completely a physical change, and the only thing you've done are to loosen up those intermolecular attractions between water molecules. So the stronger the intermolecular attraction between particles, the more energy you have to put in to change phases. Okay, so the bottom line out of that is strong intermolecular forces means higher melting and boiling points. So that's an important correlation. So if you have a container of water, again at a molecular level, and you're at room temperature, we know that water at room temperature is a liquid, right? So if you want to convert that to the gas phase, you're going to have to add heat, thermal energy, and then eventually some of the water molecules on the surface of that sample will get enough kinetic energy to essentially break free of the intermolecular attractions that hold them to other water molecules and escape into the gas phase. Chemists tend to talk about temperature of a substance and average kinetic energy kind of in the same breath because they are directly correlated. Temperature is actually a measure of kinetic energy. Okay, there's a direct correlation. So the higher the temperature, the higher the kinetic energy. So just to give you a pictorial of changing phases, again, it's typically the molecules on the surface of a liquid sample that break free into the gas phase simply because it's easier, but they have to obtain enough kinetic energy that kinetic energy is greater than the energy that holds them close to the other water molecules. This is the type of graph I have seen in the ACS final. They tend to like pictorials and graphs quite a bit, so graph interpretation will be important in 1212. So this particular graph is looking at, along the x-axis, kinetic energy, which is kind of, and has always felt odd to me because it seems like energy is usually on the y-axis. But in this case, energy is along the x-axis, and the number of molecules is along the y-axis. So let's say that in order to boil, the molecules of a particular sample need this much kinetic energy in order to escape the intermolecular attraction. So this curve shows a distribution of how many molecules have how much kinetic energy. And you can see that at a lower temperature, the peak kinetic energy lies right here. Now, of course, all the molecules don't have identical kinetic energies. It's a distribution. That's why we have the curve. But the average kinetic energy at a lower temperature is obviously lower than the average kinetic energy at a higher temperature. But what I want you to focus on for this graph is looking at the number of molecules that have enough kinetic energy to change phases. And that's represented by the filled-in area here. So if this line represents the minimum kinetic energy required to escape into the gas phase, then anything to the right of that line will also have enough kinetic energy to vaporize. And so you can see the number of, or the collective area of molecules that have enough energy to escape into the gas phase at the lower temperature, represented by this blue kind of triangular area. But the number of molecules that are able to vaporize at the higher temperature is represented by the red area. And so there are a lot more molecules that have enough energy to vaporize as you increase the temperature. So just kind of put that in your back pocket, get somewhat familiar with this type of graph in case it shows up again. When we talk about the transition from liquid to gas, we often call it boiling or vaporization, and we'll often refer to something called vapor pressure, which is another kind of odd concept. But if you have a container of a liquid, okay, and there, in any liquid, even at room temperature, in any liquid, there are a certain number of molecules that have had enough kinetic energy to escape into the gas phase. And hopefully you remember from 1211 that it is only gas molecules that exert pressure. And so vapor pressure is the pressure exerted by gas molecules that hover over the surface of a liquid. Okay? Vapor pressure is the pressure exerted by these gas molecules that have collected or hover over the surface of that liquid. So what are the things that can affect vapor pressure? Okay, well, obviously, the more molecules you have in the vapor phase, the higher the pressure you're going to experience, right? So anything that increases the number of molecules in the gas phase is going to increase vapor pressure. Okay? So the lower the boiling point, the higher the vapor pressure. Let's think about that. What's something that boils really easy? Let's say alcohol, right? If you spill alcohol on a bench, it goes pretty fast, especially compared to water. So let's say we have a container of alcohol and a container of water. Alcohol has a lower boiling point. It's easier to boil. Water has a higher boiling point. Takes more energy to boil. So which one of these is going to have a higher vapor pressure? Well, the one that has more molecules in the gas phase. Which one is going to have more molecules in the gas phase? The one with a lower boiling point, because it's easier for those molecules to escape into the gas phase. So again, the correlation to remember is the lower the boiling point, the higher the vapor pressure. They're inversely related. Just a vocabulary word for you. Something that boils at a low temperature is said to be volatile. One of the more important graphs in this chapter is a graph that looks at vapor pressure as a function of temperature. And as hopefully you make sense to you, as you increase temperature, so as you start heating a liquid sample up, the vapor pressure is going to go up also. That makes sense, right? Because if you heat a liquid up, more molecules of the liquid are going to escape into the gas phase, and those gas molecules are going to exert a higher pressure. So looking at vapor pressure versus temperature, you get, this is a really typical curves. But the information you can get out of these curves, and you will be asked this probably on one of my quizzes and tests and likely on the ACS final, is you can actually get the boiling point from one of these graphs. We call it the normal boiling point, and normal implies that it's under normal atmospheric conditions. Do you remember what standard atmospheric pressure is? It's, let's see, STP conditions, standard temperature and pressure, is 1 atmosphere, or if you're dealing with torr, millimeter, or mercury, it's 760 torr, or 760 millimeter mercury. So if you look at atmospheric pressure and you see where that intersects the vapor pressure lines, you can get the boiling point. So let's look at this for a minute. Let's look at diethyl ether. If the atmospheric pressure intersects the vapor pressure line for diethyl ether at what temperature? Well, drop down and see what temperature, and if I had a ruler, it would be at 34.6 degrees. So that means the boiling point of diethyl ether is 34.6 degrees Celsius. Do the same thing for the other some substances. Ethyl alcohol at atmospheric pressure intersects the vapor pressure curve at 78.3 degrees. And water, of course, we know its boiling point is 100 degrees Celsius. I hope. If you don't, you need to right now. So atmospheric pressure tells us that the normal boiling point of water is 100 degrees Celsius. So this is really a duplicate slide, but I put in writing what I kind of verbalized on the previous slide. I'm hoping that a couple of you, even though you may have understood that graph, asked yourself, what does boiling point of a liquid have to do with atmospheric pressure and vapor pressure? Well, to understand that, you first must get the definition for boiling point. Definition for boiling point is a temperature at which the vapor pressure of that substance equals atmospheric pressure. So if you have a container of a liquid, so we'll just imagine it's water again, and of course those water molecules, some of them at any temperature, are exerting vapor pressure. Some of them have escaped into the gas phase, and those ones are exerting a pressure. And of course, the gases in the atmosphere are always exerting downward pressure on everything. And so boiling point is defined as the temperature at which these two forces equal one another. And exactly at that temperature, when these two equal each other, so for water, that would be 100 degrees Celsius. So exactly at 100 degrees Celsius, the pressure exerted by the gas molecules coming from the liquid water sample equals the pressure exerted by atmospheric gases pushing down. So there is an equilibrium present at the boiling point, and you'll find out eventually during every phase change. There's an equilibrium, and the rate of molecules evaporating or vaporizing equals the rate of them recondensing back into the liquid. And so at the boiling point, you actually have two phases present. You have liquid and gas molecules both present in equilibrium. Not until you increase above the boiling point will it be all gas. So here's a graph for you to interpret, and I would strongly encourage you, go ahead and turn off the lecture, look at it, back up and if you need to, but try to answer this on your own. That's the best way to learn, especially in Chem 1212, is to force yourself to make mistakes and gruel through it. And then turn this back on and I'll go over the answer with you. So what are the boiling points of the three substances represented by the three vapor pressure lines? Once you identify the boiling points, the normal boiling points, I should have said. Remember, normal means at atmospheric pressure. Once you do that, see if you can give an idea as to what the identity of the substance represented by the black line is. Well, let's see. First, we have to find atmospheric pressure, which we know is 760 torr. And so we're going to estimate that on this graph. Here's 700. Well, my stylus isn't working here. So 760 is right about there. So if we drop down to the temperature, you can see the boiling point of this substance. Man, I need a straight line. Looks like it's maybe 34 degrees. And let's look at the substance represented by the blue line, 760. So it looks kind of like at the tip of each of these lines, which isn't usually the case. And this one is really close to 80 degrees, maybe 79 degrees. And the black line is right at 100. So knowing that, I bet you can estimate, hopefully, that the substance represented by the black line is probably water, because we know the normal boiling point of water is 100 degrees Celsius. So now we're going to get ready to do some calculations with phase changes and determine or calculate how much heat is required to actually change the phase of a substance. So the amount of heat energy or thermal energy required to vaporize exactly 1 mole of a liquid is called the heat of vaporization. And it's symbolized delta H, and then the subscript is VAP for vaporization. If you think about it, when you vaporize something, that's an endothermic process, right? It requires the absorption of energy in order to occur. Vaporization is always endothermic. So the sign for the heat of vaporization is always positive, as all endothermic processes are. And just to let you know, if we ever happen, and we will, to be talking about the reverse of vaporization, which is condensation, that means going from a gas to a liquid, condensation would always be exothermic, okay, and would have the opposite sign. In this case, would be a negative. All right, so now let's look at the heat of vaporization for several liquids here and see if we can find any patterns. The main thing I want you to notice here is that as the boiling point increases, the energy required to vaporize a substance also increases. Makes sense, right? If it's harder to boil, it's going to take more energy to vaporize it. Makes total sense. And I hate throwing this rather complicated equation in at this point, but it turns out that that definitely shows up on the ACS final. I used to leave it out of my course, but I don't want to just leave something out I know that you may need. So there is something called the Clausius-Clapeyron equation, which I'll show you written out in the next page. But the bottom line is it tells us that if you plot the natural log of vapor pressure versus the inverse of temperature, 1 over T, you do get a straight line. Whoop-de-doo, huh? Why do we care? Oh, actually, you guys do a lab with this too. 1212 has a lab that uses a Clausius-Clapeyron equation. Well, the reason this is important is because the slope of that line gives us really important information. It gives us delta H, okay, heat of vaporization. And that's an important kind of constant to know about every substance. Now, just a little note here. Anytime we're talking about any type of energy, which is heat, light, whatever, the units are like joules, kilojoules, something like that. So let's look at the Clausius-Clapeyron equation being used. This is the form of the equation that you will usually see, and it's called the 2-point form of it. Well, basically, you're just taking 2 points off of that graph I just showed you on the last slide, and from those points you're estimating the slope, okay? So typically you'll be given 2 temperatures and 1 pressure and be asked to solve for the second pressure. So you got to kind of hone up on your algebra math skills, okay? So this might be a good problem for you to practice. I have an example down here. So water has a vapor pressure of 24 millimeters of mercury at 25 degrees. So I would go ahead and label what these stand for, right? Millimeters of mercury is a pressure. We'll just call that pressure 1 and temperature 1, okay? Look at this equation. And heat of vaporization, oh, they're giving us delta H, okay, of vaporization. What is the vapor pressure? That's pressure of water at 67, okay? So they're asking us to solve for P2, okay? And here's T2. So this type of problem, the first thing I do is just what I did, is go and label what everything represents according to the equation. Now, even though I haven't worked one of these for you, unless you're totally overwhelmed, I would try plugging these values into the Clausius-Clapeyron equation and see if you can solve for P2. Again, it's algebra skills, but I want to point out to you that in almost all of these calculations, temperature must be in Kelvin. Notice that A lot of times they're given in Celsius. Do you remember how to convert from Celsius to Kelvin? So you take degrees Celsius, you add 273, and that gives you Kelvin. So go ahead and try that equation, mess around with the math yourself, and then I will go through the answer on the next page. All right, so here we go. We're going to plug in the value they gave us for P1. Remember, that was 24 millimeters of mercury. We are solving for P2. That's what we're trying to find out. They gave us the energy for heat of vaporization, 40.7 kilojoules. And since, okay, boy, that's a little bit hard to see. Those are units there. Okay, 40.7 kilojoules. Now the R value, that's the universal gas constant, which is equal to 8.31 joules. But since your units need to match, and since delta H was given in kilojoules, you need R to also be in kilojoules. So to convert from joules to kilojoules, right, there are 1,000 joules per 1 kilojoule. And so that's where the 8.31 times 10 to the minus 3 kilojoules comes from. All right, temperature. Make sure you convert the Celsius given to Kelvin. So now even if you didn't plug in these values correctly, I encourage you to take this equation with the numbers I've already plugged in and do the math on that. Number one, to make sure you're using your calculator wrong, and number two, for some reason these inverse ratios mess students up like crazy with their calculator. So I would make yourself go through that and make sure that you solve for a pressure of 182. This page starts the more standard calculations that I will be expecting you to do from chapter 11, and it's using something called a heating curve. Okay, so when you see this type of lines, diagonal straight lines and then a plateau and then another diagonal straight line, that is a heating curve. So along the y-axis is temperature, along the x-axis it's typically called heat added, or sometimes they just say time of heating. Same thing. And so I'm going to lead you slowly through here, but there's one type of calculations that you use for the sloped areas and a different type you use for the plateau areas. The first thing I want to point out to you is that if you start heating a substance, the temperature, you would expect the temperature to increase, right? So this slope line is no surprise. What is going on? How can you be heating something and the temperature not be changing? Where does this plateau come from? It turns out that during a phase change, during any phase change, whether it's melting or boiling, subliming, whatever, temperature stays constant until all of it has changed phase. And then the temperature will start going up again. So that's important to understand. So let's interpret this graph. So let's say that we have a solid material, and we're going to start at negative 10 degrees Celsius, and we're going to start adding heat. So the temperature of that solid is going to increase, then, all of a sudden the temperature stops changing at 0 degrees. So that is the melting point of the substance. So it's probably water that we're talking about, right? Because melting and freezing are the same thing. If you didn't already realize that, they're the same temperature, only opposite directions. So water freezes at 0 degrees, ice melts at 0 degrees. Okay. And any phase change has two phases present. They're in equilibrium with each other. So at the melting point, you have liquid and solid present. Once all of the solid ice has melted, the temperature will start climbing up again. So I just want to emphasize that every phase change is an equilibrium that involves two phases of matter. So for example, if we're applying heat to a sample of liquid water, at the boiling point, remember the boiling point is when the pressure exerted by the vaporization of the water molecules equals the downward pressure of atmospheric pressure. So anyway, at the boiling point, there's an equilibrium, and the rate of vaporization equals the rate of condensation. So here's an entire heating curve, and again, this is for water. That's just a convenient one to use. So it turns out, because you use different equations for the sloped areas of a heating curve than you do for the plateau areas of a heating curve, we have two different equations you need to learn and be able to use. If you want the total heat added to do a process, you've got to add all these segments together, calculate them separately, and then add them together. By the way, make sure you can interpret this graph. Make sure that you could actually recreate this graph. If I told you to draw a heating curve for water, you should be able to do it. You know that the melting/freezing point for water is 0 degrees, so your first plateau would be there. You know that the boiling point of water is 100 degrees Celsius, and so your second plateau should be at 100 degrees. So make sure you could create one of these if I asked you to. Now, as a reminder, during a phase change, you have two phases present. Okay. Oh boy, what did I do? I messed this up. Down where it's really cold is the solid phase. So in the sloped area, there's only one phase present. When you have a phase change, there are two phases present, solid and liquid. I must have cut and pasted and not corrected. Okay, so then when we get to a sloped area, we only have one phase present again. And the next plateau, again, we have the two phases in equilibrium. So let's see. So here we would have liquid and gas at this plateau. And then the slope area is just gas. Vapor is another word for gas. They use them interchangeably. For the sloped areas, the areas that change temperature, the equation we use I call the QMCAT equation, okay? Where Q is the amount of heat, and that's usually what you're solving for, the amount of heat required to change something. M is the mass of the sample in grams. C is a specific heat capacity. If you're funny on that, if you're fuzzy on that, you might want to go look that up. That's relatively important. We went over it briefly in 1211. Don't get capital C confused with Celsius. So degrees Celsius is a temperature reading. Okay, just big C by itself is specific heat capacity. And that just tells us how sensitive a substance is to changing temperatures, to temperature fluctuations. And then, of course, delta T is change in temperature. So if it's a sloped area, you're going to use the QMCAT equation. We have another different equation we use for the plateaus. If you're going to do a calculation, you typically will be given the specific heat of a substance. I want to point out, this is kind of weird, but let's say you're doing a heating curve for water. The specific heat value for ice is different than the specific heat for liquid water, which is again different from the specific heat for gas. So got to be really careful if you're looking at a table of values. So here's a sample problem. How much heat is given off when an 869 gram bar of iron metal cools? Okay. So we presented it as a heating curve, but you can have a cooling curve. So in a cooling curve, you start at a high temperature. So you're going to start up high, and the temperature is going to change until it cools or changes phases, and it's going to flatten out. And then the temperature will change again, and it flattens out again. Now, one of the things I didn't mention in this problem, in this question, which I should have, is that iron remains a solid throughout this problem. Okay, so we're not doing any phase changes, but you would have to be told that. You would have to be given the melting and boiling points of a substance. You may have guessed that a bar of iron is solid at these temperatures, but I would tell you in a problem anyway. So we're only on a sloped area. Okay, so we're in a sloped area, so we don't have to do two separate calculations. We're only using MCAT. So again, you have the mass of the substance. You were given the specific heat of iron. Notice the weird units for specific heat. It's the amount of heat joules required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Weird units. Anyway, and delta T is the change in temperature. Typically, we think of delta T as T final minus T initial, and so that gives us a negative value for delta T, which means the Q value, or the heat released, is minus 34,000 joules. Okay. Remember what that when you see a negative sign on an energy, that means it's exothermic. I'm not sure if you realize this, but when you cool something, it's releasing heat. So that's an exothermic process. So that's just a really, really simple example of using QMCAT. So now we're going to move on. In the plateau area of a heating or cooling curve, there's no temperature change. So you cannot use MCAT, all right? If there's no temperature change, if the temperature change is 0, this equation becomes meaningless. So if we want to calculate how much heat we have added or taken out of a substance during a plateau, we have to use these values called heat of fusion, which I kind of mentioned briefly a few slides ago, or heat of vaporization, depending on the plateau we're looking at. So just again to go over the definition. Heat of vaporization is the energy required to vaporize 1 mole of a liquid substance. Heat of fusion, I don't know why they don't call it heat of melting, because that's what it is. Heat of fusion is energy required to melt 1 mole of a solid substance. So basically, if you're calculating the heat involved in a plateau area, you're going to simply take the heat of vaporization or the heat of fusion, whichever plateau you're talking about, and the units for that will be either joules per gram or joules per mole. It just depends on the units they want to give you. And all you do is multiply that given value by how many moles you have or how many grams you have. Again, you've got to look at the units to know whether you multiply by grams or moles. And so I'm being redundant, which I tend to do. The definitions for heat of vaporization and heat of fusion. And again, vaporization and melting require input of energy, so their signs are always positive. The reverse of those processes, so the reverse of melting is crystallization or resolidification, and the reverse of vaporization is condensation. So just know that the mathematical sign for fusion is the opposite of the mathematical sign for crystallization, and same for vaporization and condensation. A little tidbit that I have seen show up as a multiple choice question is that the heat of fusion or the heat of melting is always a whole lot smaller than the heat of vaporization. Do you think you could explain that in a short essay question? So think for a minute. If you turn the lecture off for a minute and see if you can come up with an idea. Why would the heat of vaporization, the energy required to vaporize 1 mole of something, be so much more than the energy required to melt something? It turns out, remember what you're doing when you're changing phases? You're just loosening the intermolecular attraction between molecules. Well, when we're melting, we don't have to completely separate the molecules, right? We just loosen them a little. Moving from solid to liquid is just loosening the hold between the molecules just a little. But when you vaporize something, going from liquid to gas, you have to really yank these molecules away from each other. So you've got to put a lot more energy in to vaporize something. All right, so here is a mammoth problem, and one that would probably be a free response problem on your next test. What is the total heat? So you're going to have a bunch of Q's that you add up to convert 18 grams, that's your mass, right? I like to label everything, of ice. So you're starting in the solid phase at a temperature of 25 degrees. I think I meant minus 25. I did mean minus 25. So converting ice from minus 25 degrees to 125 degrees Celsius steam. All right, so let's look at a heating curve. If you're not given a heating curve, you need to generate one. So we're talking about H2O. So we know our first plateau is at 0 degrees, and our second plateau, the boiling point, is at 100 degrees. So we're starting at minus 25, and the first calculation, we're going to call it calculation 1, is on a slope, and it's going to be using the QMCAT equation, right? Because all sloped areas use that. Then we have a plateau for when it melts, and that's going to be using delta H of fusion. Remember, fusion is melting. Then we have a sloped area again for the liquid, where we can use QMCAT again. And finally, the energy required to boil, which is, we're going to be using delta H of vaporization. Oh, not finally, I guess. We have one more step. You could have as many as 5 steps in these problems. Isn't that awful? So the last slope is going from the boiling point, which is 100 degrees, up to the final temperature, which they said is 125. Since it's a sloped area, it's QMCAT again. That's 5 calculations, and then you have to add them all together. If you feel brave and you want to get an A in this class, I would shut this off and see if you can do that. Calculation 1. That was in the first sloped area. That's going from minus 25 degrees Celsius up to where it plateaus, which is the melting point at 0. So we simply plug in the mass times, that's 18 grams, times, oh, I just realized I did not give you the specific heat capacities in this problem. I should have. They're in your textbook, so you can just go along and watch me work this one out. But I would always give you those constants in a problem. Specific heat capacity of ice is 2.09. The change in temperature is 25 degrees. If you go TF minus T initial, final temperature is 0. The initial temperature is minus 25. All right, so if you plug all that out, you get 941 joules of energy was required to heat that block of ice up to its melting point. Calculation 2, we are now at the plateau. So the heat we're going to calculate uses the heat of fusion or melting for ice. And depending on the units you're given, okay, so these units are per mole, which means we have to multiply that value by the number of moles we have. Well, we were given grams of ice. How do we get to moles? Okay, so you need to divide by the molar mass of water, which is 18.02 grams per mole. And that will give you the moles of water, essentially 1 mole. So, sorry. One thing I'll point out too is sometimes the constants they give you are in joules and sometimes they're in kilojoules. But at the end, before you combine all these Q values, make sure that they're either all in joules or all in kilojoules. Step 3, where are we? Let's see. We have done the heating the ice. We've done melting, and now we are heating the liquid water. And let's see, melting was 0 degrees, and so we're going to heat that liquid water until the next plateau, which is 100 degrees. So the specific heat capacity of liquid water is different than the specific heat capacity of ice, so be careful of that. We still have 18 grams. Here's the specific heat capacity of water. The temperature change is going from 0 to 100. So the amount of energy required to heat up 18 grams of liquid water from 0 to 100 is 7.52 kilojoules. Almost done, guys. All right, so now we have heated up ice, we've melted it, we've heated up the water, and now we have to vaporize those 18 grams of water. It's a phase change, a plateau, so we have to use heat of vaporization. Make sure it's heat of vaporization, not heat of fusion at this point. That is 40.7 kilojoules per mole. Remember, heat of vaporization is always really high. Units are per mole, so we got to multiply by the number of moles. We just calculated on the last slide that we have 1 mole of ice. So the heat in this fourth segment, the plateau, is 40.7 kilojoules. The fifth and final calculation, after we boil the substance, we can heat up steam further. That's why steam is more dangerous than boiling water, by the way, because steam can get hotter than 100. So we're at a sloped area. We can use QMCAT. We're starting at 100 degrees Celsius at the boiling point, and they continued to heat that until it reached 125. So filling in for QMCAT, you've got to know the specific heat capacity of water vapor. Plugging everything in, you get, that's not very much energy required to heat the steam up. Now you have to add all the Q values together from all 5 calculations. Make sure that they are either all in joules or all in kilojoules. When we add them all together, we get that there are a total of 55.2 kilojoules required to heat 18 grams of ice from minus 25 all the way to 125. Big, huge problem. Likely to be all or part of that, likely to be a free response problem on your first exam. Here's one that I really want you to try, even if it means you have to back up and watch me work that problem again. You have a 25 gram sample of ice, but this time we start at 0 degrees. Okay, so we don't have any of that going on. We're going to melt it all, and then we're going to warm it, but only to 20 degrees. Okay, can you figure out how many calculations you need to do? So think about that. Try to do the calculation, and I will work it out on the next page for you. That problem required only 2 steps. Step 1 was to completely melt the substance. It started at 0 degrees, but it didn't say it was melted, so you need to melt it all. So you're traversing the first plateau. So you're using delta H of fusion, which in this case was given per grams instead of per mole. So now you get to multiply it by the grams. Step 2 then was, let's see, we had melting, was then heated up, but only to 20 degrees. So when it melted, it was at 0, and then we heated it to 20. So it's a slope area. We use MCAT, plug in all the information, and then add the different heat values together. And we get that the heat required is 10,467 joules. That is it for this mammoth second lecture from chapter 11.